Thank you. We'll begin with a word of prayer. So, dear Heavenly Father, we thank you again, Lord, for topology, and we just pray that today we be able to understand what we cover, and that you just bring insight to us as we study Minetti today, Lord. In your name I pray. Amen. So I'm going to pick up, I think, more or less, we're to section 6.4. I mean, the last section was Cauchy sequences. I suppose some of those things I showed you in like advanced before. Proposition 6.29 might be new. A subspace in a complete metric space is closed if and only if it's complete for the induced metric. It's kind of interesting, right? So there's that. I have a little bit more to say about complete when we get to the completion section, so I'll kind of wait for there. Okay. One of the things that was kind of interesting is when Min came back from his, where do you go? He went to this, I think it was the Mass, which is at Penn State. You know, he came back and he had basically taken a semester of graduate math, and one of the things he was taking was kind of like a baby functional analysis course, and seemed like a lot of what they were thinking about was this totally bounded thing. I mean, he was just all excited about total boundedness. So we now get to join Min in his enthusiastic study of the totally bounded things. So here's the definition. Totally bounded is yet another tool to look at things. A metric space is said to be totally bounded. Totally bounded. If it can be covered by a finite number of open balls of radius r.
Almost sounds like compact.
Doesn't it? Yeah. Almost. Finite number of open balls of radius r for any positive real number r. Okay, so his opening comment there is each totally bounded metric space is bounded. Because if X is the finite union of balls, say X1, X11, I guess I can't help but write here. Forgive me if I do some writing. So it's like, okay, so if you got like that was supposed to be a ball. Sorry. So he's just like each radius 1, right? Those were the same size. Sorry. Yeah. And M is the maximum distance between any two centers. Then by the triangle inequality, the distance between any 2 points of X is at most M plus 2. So this point is like if these are the furthest ones apart. Right, if that's M.
And then you go to the edges too.
Yeah. Right, exactly. Then if you were to, that would be, what would you say, 2M plus, no, you say M plus 2? Right, yeah. Of the midpoint, right? I think that's, and then all of the all these balls would be contained inside the other one, and so it would be bounded. Right. That makes sense. Lemma. Let me erase my nonsense picture. Lemma 6 point. 6.31, every sequentially compact metric space is totally bounded. Every sequentially compact metric space is totally bounded. Every sequentially compact space is totally bounded. What did I say? Lemma. 6.31. Manetti as usual. All right. See if we can understand the proof. So what he does is he says, take the, let's see here, proof. Consider metric space X with distance function D, all right? Sequentially compact. What would that mean?
Every sequence has a convergent subsequent.
Right, something like that. What you said. And suppose by contradiction, X cannot be covered by finitely many open balls of radius R. All right, then what? He says, we construct recursively a sequence A sub n. Interesting. So how is he going to construct this sequence? He says, choose A1 just to be some arbitrary point in X. So let me draw a picture. Here's X. Here's my point A1. All right. And then for any n greater than 1, let A sub n be some element in the non-empty closed set X. And what's he removing? So he
The open balls around each element that you already have.
Right, so we start by the A, so like A2 is just going to be, you pick anything you like.
Whatever's outside of that ball.
Yeah, so we look at the R ball around here, like so. And then A2 is just anything out here. And then you surround that with an R ball. And then you pick an A3. Then you surround that. And each time you're picking something that's not in the union of all the balls up till that point.
Do the balls themselves have to like intersect?
No.
They could. They don't have to.
They eventually will, I think.
What's that?
They probably eventually will.
I didn't know if it was like, since it was like sequential, like you had to build it.
Well, like I could not pick, I can't pick any of the points that are inside the green dotted circles as we go
Yeah.
on. And so forth. So basically A sub n is an element of X minus the union of the balls centered at A sub,
I.
yeah, A sub I radius R.
For I equals 1 to n minus 1.
Very good. So that's, and so you keep going like this. What does that do? Well, that creates a sequence, right? And since, notice that the distance from A sub n, comma, A sub m is greater than or equal, and by the way, I've been drawing them like they have to be close by points. That's not the case. I mean, it could be, I mean, it could do all kinds of crazy junk. But the point is, that can never stop. if that was to ever stop, if there ever was to be no point left to go to, that would violate our assumption that it cannot be covered by finitely many open balls. Like if the sequence ever stopped, that means you've run out of points.
Yeah.
At that point, you can say all the green circles up to then is a covering by finitely many open balls. So you can then therefore argue that the distance from A and AM is greater than or equal to R, right, for every n greater than m. And so no subsequence of A sub n can converge. Now, the reason this makes more sense to them is they're taking reals right now. They've been playing with subsequences some.
I think I can kind of see it though.
Yeah.
It looks nice.
There might be a case to be made that we should spend a day or two in Calc 2 on subsequences. It might be wise. It's a little bit above the level where we typically do things in there, but there's a whole host of examples that you can't solve unless you consider subsequences. When you consider subsequences in terms of studying convergence, it strikes down a whole host of problems that you can't touch with regular convergence theorems.
Do you not already, though?
Hmm?
Do you not already, though? In Calc 2?
I don't know. Is it in the book? I'm covering the book.
I don't know. I mean, last semester I had some people come in for Calc 2, and they had problems with subsequences.
Yeah.
So
We did that
Woo!
with Kester.
All right. I don't know. I have not previously because in Calc 2, Calc 2 especially, my teaching has evolved from, I just pretty much was what everybody else do in Calc 2. That's where I started because I was a grad student. I didn't know anything else, you know. And then as time goes on, I'm kind of looking around, seeing what other people are doing and finding out how tight can I turn the screws. And then at some point I stop caring what other people do and I just say, you know what, I'm going to do whatever I want. And then that's when it gets really ridiculous. But that's
sounds like a good teaching philosophy.
that's where the goodness is. I mean, I read teaching journals and I study modern methods of pedagogy and I survey my classes to find out what the students want, of course.
We had that yesterday for one of my engineering classes.
Gosh. Let the inmates run the asylum. What kind of nonsense is that? I tell you. Anyway, I mean, if my teachers listened to what my fellow students want, we'd have never done anything. I want my professors not to listen to the slackers in my class. I want them to cover everything that they can. I want the biggest bang I can get for my courses. I mean, come on. Personally. Anyway, I'm not taking courses anymore, so whatever. Except for this one. I'm kind of taking this one with you guys. Oh, okay, so there you go. There's proof. That'll probably be the last thing I prove here for a while. Oh, maybe I'll prove this next one. I don't know. Lemma. 6.32. Every totally bounded metric space is second countable. Or for you Trump supporters, two countable. Alright.
Now also according to Ben Carson. Sorry, I should know.
According to what?
I know, according to Ben Carson as well.
Oh. So he woke up? And he supported Trump, huh? Okay, good.
Yes.
I don't understand how anybody could... Whatever. It's supposed to be like, you're the leader of the free world. You're supposed to be a good communicator. Come on, man. Sorry. He's a good man. Well, so is my father, but he shouldn't be president, you know? All right. Let X be totally bounded. Totally. Sorry. If I offered bonus points for coming in with a man bun, do you think I would get any? Not for you guys. Just like in physics, just to see.
Maybe.
It's disturbing. It's like I walk around and there's like samurais in the hallway.
If you were to ask that of 201 or 202 instead of 231 or 232, you'd probably get some takers.
I wouldn't have to ask. They'd just be there. That's right. I digress.
Give them extra points if they walk around with samurai sword.
Yes. I got my samurai umbrella. It's in the car right now. It's probably a bad choice for today. Anyway, x be totally bounded. What does he say next? For any n, there is a finite subset E sub n such that what? For any n in the natural numbers, there exists a finite subset En, subset of x such that what? It says x is equal to the union. I better use this notation here. Union of balls at E, comma, the radius 2 to the minus n, such that what? Such that E is an element. What is he doing? Let's see, to show it's second countable, what do we got to do?
He's showing that it's separable, which implies that it's second countable.
Okay. What is it? So what do we need to show it's separable?
It's a countable basis of open sets.
Countable dense subset.
Countable dense subset. That was separable.
Yeah.
All right. Why does there exist this totally bounded means we can cover it with finitely many open balls of any radius we like, right?
So we're choosing 2 to the minus n
Okay.
and covering it, and then just taking like the centers of all of those balls to make En. Or, yeah.
And that's our basis. Right?
Not quite.
So the ENs are just the centers. The EN is the center, the collection of centers for the balls.
Yeah, for a certain radius. And then he goes on and takes the union of all that.
That has to give us the whole thing. Okay. Yeah, that makes sense. That makes sense. And then his argument, of course, is that this is countable. Well, if you look at the set E, which is just the equal to the union of the E sub n's, is countable. Oh, you be quiet. Countable, dense, countable, and is thus dense. Why is it?
Well, it's dense because for any point you pick an x, you can find an E that's in the set E and a ball that'll contain that point, which shows that it's dense.
Ah,
Yeah. We can find a ball of small enough radius and an E that's close enough to it, I think.
okay, so then it follows that x is separable. And then that implies through our lemma 6.7 that it's second countable. Because lemma 6.7 said,
Separable. That's second countable.
yeah, separable.
In a metric space, I think.
Yeah, in the metric. Everything's in a metric space at the moment, right?
Yeah.
Any separable metric space has a countable basis. So, yeah. The engineers call this the red square. Because I got Russians to the left of me and Russians to the right of me. But they're not, I don't know if they're really Russians or if they're just Russian enthusiasts. So,
The name Red's still.
I could find out for sure. I need to bring a hot plate and make some hot cakes, or pancakes as you know them. If they're truly Russians, they would come to my office and say, "What do you have here?" And they would demand some. In my experience,
The band.
a surefire way to get Russians to come to your office is to make pancakes.
I think you get a lot more Russians.
Yeah.
Yeah, that's probably true. Undergraduates, it would call them into, wouldn't it? Okay, so let me get to the main point here. Your suspicion about isn't this just like it being compact is a very good suspicion. Here's theorem 6.33.
Oh, you were talking to me.
Yes, I was talking to you.
Sorry.
It's okay. In a metric space, the following X, the following be equivalent. Find R equivalent
Should
there.
have put a B.
Should I put a B?
Yeah.
The following be equivalent. Yeah, there you go.
Ah, no need to
It's
change
like
it.
it's the street version. 1 X be compact. 2 every sequence in X has a limit point. Sorry, I seem to have drifted into proper grammar again. I'll make up for it in the next one. 3 X be sequentially compact. And finally, last but not least, 4 X is complete and totally bounded. I actually think this proof is a lot like the one we've already just done. I'm gonna go ahead and go on here. I just want to kind of try to stop and appreciate it for what it says, right? So it basically, and if you're in a metric space, you have these different concepts that capture the same idea. We can either talk about compactness, every open cover having a finite subcover, right? Every sequence has a limit point, as we defined last time, right, in terms of neighborhoods. Sequential compactness, that means that every sequence has a convergent subsequence, right? Or it's complete and totally bounded, which is perhaps the most geometric of any of these, right? Like this idea that you can find a finite number of open balls of radius r that covers the thing for any finite radius r. Actually, when I think about compactness, I think about totally bounded. Honestly, that's my mental picture of compactness. But that's because I usually drift towards thinking of metric spaces. Right? This totally bounded idea wouldn't make sense if we weren't in a metrical context, right? What would a ball of radius r mean in, Zariski topology? I don't know. Wouldn't mean much. Lemma 6.34 says the following. A subspace A in a metric space is totally bounded if and only if its closure is totally bounded. Let's see here. Another few just comments about subspaces. A subspace A in a space X is relatively compact if it's contained in a compact subspace of X. So if you had B, all right, subset of X, and suppose B wasn't compact, all right, for whatever reason. Maybe it's bounded, but it's not closed, you know. Then if there's, you know, so B might look like, right? Then if there's an A, like that, which contains it, and if A is compact, then we say that B is relatively compact. For example, any open ball would be relatively compact, even though it wouldn't be compact. And here's what he says. He says, when X is Hausdorff, A, a subset of X, is relatively compact only if its closure, if and only if its closure is compact. So like, kind of even, I mean, you can see it in my stupid picture. If its closure is closed, so if you're in a Hausdorff space, what do we have in a Hausdorff space? We have, in Hausdorff, do we have closed and bounded? I don't know if I've bounded here. In Hausdorff, does closed imply compact? What was the deal? What was our big theorem about compact subspaces of Hausdorff spaces? There must have been a theorem that I should remember. Gotta use the Wayback Machine here. Come on, still going. Any compact subspace in a Hausdorff space is closed. Would seem to be compact implies closed. Well, it says any compact subspace in a Hausdorff space is closed. I think that's a kind of, that says that it's if and only if, right? I mean, that wording. So that's corollary 4.48 on page 77. So if you, of course, if you take the closure of a set in a Hausdorff space, you get a closed set, which is consequently compact. So any, so that means relatively compact in a Hausdorff space, if and only if the closure is compact. In other words, well, I mean, the closure is always closed. The question is the closure compact or not? And then corollary, that's a definition, of course, but corollary 6.36, a subspace in a complete metric space is relatively compact if and only if it is totally bounded. Subspace is in a complete metric space is relatively compact if and only if it's totally bounded. Right. So, for example, in a complete, here's a complete. Well, here's a silly indication of a complete metric space. How about this? X equals to R2, right? We could look at different kinds of subspaces, right? And they're only going to be relatively compact if they're totally bounded. And so basically that's just a question, more or less, I mean, I think pretty much just a question, is it a finite space, is it, or does it go on and on, you know? Like certainly a line is not totally bounded, right? Because, I mean, it takes infinitely many of them, right? Of any particular radius, so it's not finite, it's not totally bounded. But on the other hand, if you have anything, even if it's some kind of weird mess of whatever noodly goodness, you know, you can always, as long as it's got some finite size to it, you can cover it with finitely many open balls of any radius you pick. Could be a kabillion of them, but still finitely many. Didn't have to, they had to be a small finite number, and that kind of thing would be relatively compact. That's a lot of things. Of course, it could be other less weird things like open disks or triangles or rectangles or whatever. Float your boat. I want to be a triangle. Sorry. Baire's theorem. Or have I said that wrong? My resident French scholar.
That's pretty close.
Pretty close. Okay.
The Bears.
Yeah.
The Bears.
The Bears.
No, Jess.
Sorry, I had to.
Will you give me the correction?
Baire.
Ah.
So you gotta
Then I'll start coughing. It's gonna have to stay Baire. Yeah. I see why men got excited about this concept of totally bounded. It's so geometric, you could ask students really difficult questions and they'd still have a hope of kind of reasoning their way through it, right? It's a great definition and concept to play with. So here's the definition, and this definition I won't even pretend to understand. I'm at the start of this, guys. A subset of a topological space is said to be nowhere dense if its closure has an empty interior. So let's give a name to this subset. Let's call it, say, U. If the closure of U, the interior of the closure of U is empty. And it's said to be meager if it is contained in the union of countably many nowhere dense subsets. I don't think that many is a technical word. Let's see here. So let's say V sub I is nowhere dense for I in the natural numbers, right? And then so U must be a subset of the union over I and the natural numbers of V sub I, something like that. Of course, it could be that we just have finitely many nowhere dense subsets V sub I. There it is. Now what he says to warn us to start with is that being dense or meager is not an intrinsic property. It depends on the ambient space. So to start with, the point 0, all right, is nowhere dense. Does that make sense? Let's see here. If you take the
closure, it's just going to be itself since it's close in R and it has no interior.
There's no interior.
yeah, okay. But if you take U equals to 0, the singleton 0 in topological space of the integers,
It's going to be open. Well, yeah.
with the, I guess, the discrete topology we're using, right? So the closure of U is still that. But since we're working with the discrete topology, that's also equal to, the interior of 0 is also, oh, Yeah. It's meager if it's contained in the countable union. I don't think there are any nowhere dense sets. Right? I mean, is it possible to have a nowhere dense set in this stupid discrete topology?
I don't think so.
Like, absolutely everything is an open set, so it's just dumb. There are no I don't even think there is such a thing as a meager subset of the integers. It looks to me like it's not even possible. We may rather punningly, I'm sorry, I don't know what's coming here. Distinguish meager sets into two categories: the truly thin and slender subsets, and the false lean ones. The former have an empty interior, while the second sort do not, albeit still being meager. Something's lost in translation here. I think this is a joke about people who are fat versus about people who are skinny about people versus people who are really skinny, or something like that. I don't know. Some kind of Spanx joke here or something. I'm not sure what this is. Anyway, Baire space is a space that has no subsets of the second type. All right, let me just forget his joke and state the definition. Definition: a topological space. X is a Baire space if each meager subset, I can't spell meager.
Use it again. Go on. Is that like?
Yeah, I don't know. I almost wonder if this should be,
I think it's ER.
Yeah,
but the book has
yeah.
RE. I mean, this could be a translation thing.
Yeah.
I haven't researched
It also
what the
says
canonical
whence.
spelling is. It's kind of like,
A book that also says whence might as well spell meager with RE.
hey,
I think it's.
whence is a good word.
What's the good one?
Whence are you saying otherwise?
Not confusing.
Sorry.
It's okay. It's fine. Each meager subset has an empty interior. Yay, integers are Baire spaces. There are no meager subsets. To check such a property, it obviously suffices to show countable unions of nowhere dense closed sets have non-empty interior, or equivalently countable intersections of open dense sets are dense. The empty set is a Baire space. A non-empty discrete set is a Baire space. Yeah, we got that one already. Well, I got the integers. You just got the rest of them. The only nowhere dense subset is the empty set. Okay. The rationals are not a Baire space. So let me get to the example. Q, he says Q, not Baire space. Why is that? He says every point is nowhere dense and closed. So if we look at a singleton in the rationals, right, P over Q, the closure of that is P over Q, I believe.
Mm-hmm.
I'm supposing we're using the rationals with the metric topology, as we can do. And the interior, of course, of this is what? Well, what's the problem? I'm sorry, I'm missing something here. The interior of that is what? Well, what is the interior? I guess it's still empty, isn't it? I mean, there's no Maybe I don't understand the rational topology much. What do you think about this one? He says every point is nowhere dense and closed.
Maybe it's not the discrete topology, maybe it's the subspace topology in R.
That's what I was hoping
That was-
for.
yeah.
Yeah, so like,
So then it's this, so then it's the same thing as like the real numbers.
so if there's on the real line, right? Typical open sets,
Mm.
stuff like that, right?
Right, so each point is going to be closed. And just like in R, it's also going to be nowhere dense. But then Q is going to be a countable union of these nowhere dense sets.
Ah.
But it doesn't have an empty interior. Or, I think.
He says a topological space is a Baire space if each meager subset has an empty interior. What is the meager subsets of the integers? U is meager if it's contained in the countable union of many nowhere dense. So every singleton is nowhere dense, but the whole rational numbers is the countable union of these singletons, right?
So it's meager.
So the rational numbers itself is meager.
I guess.
And of course the interior of the rational numbers is not empty. The interior of the rational numbers
Is
is
the rational.
the rational numbers,
Yeah.
it's certainly not empty. Okay, so yeah. Because it has to be each meager subset. So in particular, you can look at the whole rational numbers as the subset from which it
Yeah, as long as
fails.
you find one.
So the interior of P over Q is still P over Q.
No, it's empty.
Okay, it's empty.
Yeah, I mean, because the interior would have to be all points for which there exists a open interval of rational numbers. It's like an open interval intersected with rational numbers. So this isn't an accurate picture of the open interval in the Q. The open interval in the Q, relative to the subspace topology, is like, of course, I would be here the rest of my life to try to put all of them in there.
Yeah.
You know, they're dense. Okay, so here's the theorem. Here's Baire's theorem. Yeah, put it here. Ooh, ow! Sorry. I was trying to say that. Theorem. 6.40. A topological, I'm an idiot. Complete metric spaces. Complete metric spaces are locally compact Hausdorff spaces. Complete metric spaces and locally compact Hausdorff spaces are Baire spaces. So we already noticed the reals, right? We've already seen that the rationals aren't, because the rationals are not a complete metric space, right? And then the proof here, I have not the energy to do this proof. The proof is rather this. You have to pay me to do this proof. It's involved, right? I don't think it's out of your reach though. If you devoted an hour of your time, you probably understand it. Remark 6.41 is probably worth reading. The two statements in Baire's theorem here are completely independent. there are compact Hausdorff spaces that can't be metrized by any distance. And there are also complete metric spaces which are not locally compact. For example, the infinite dimensional Banach spaces, like the infinite dimensional Banach spaces. A little bit of history here. René Baire, 1874 to 1932, is also known for introducing in 1899 the notion of a semi-continuous function, and for proving that lower semi-continuous functions defined on a closed and bounded interval have a minimum. So it's kind of a more technical and substantial version of the extreme value theorem. And then he concludes this section with a technical thing about a countable family of subsets in Rn. When the proof is that Rn is a Baire space. It's like, haha! Behold the power of the Baire space. Okay, point has been made. Next, we move on to the section of completions. All I really want to do there is state for you the definition. I think the definition alone is worth, like, just see the definition, understand the idea of the definition. That should probably more or less suffice for us. There's a larger discussion to be had here in the context of like measure theory, to studying like sets of measure zero, and I think this is where those sorts of ideas, because this is starting to get towards that idea of finding some subset. To me, it feels like a little bit like the idea that you come across in measure theory, looking at these sets of measure zero that you can more or less ignore in the integral. But that's for another day, not in here probably. So here's the definition. Let xd and x hat d hat be metric spaces. Okay. A map phi such that x goes to x hat is called a completion. Of xd if what? Few conditions have to hold. Number one, phi has to be an isometry. What's an isometry?
Mapping that preserves the metric.
Exactly. So d hat of phi of x, phi of y should be equal to d of xy, right? For all x and y and x. Also, why is it called a completion? Because the x hat, d hat, is a complete metric space. Three, phi, and this is to keep it from being dumb. So that alone is not quite enough. Like, you also want that x is almost all of x hat. And that's where this comes into play. Phi of x is dense in x hat. Of course, the standard example is what?
Rationals and the reals.
Rationals and the reals, that's right.
The inclusion map.
And the identity map. So we have phi from the rationals to the reals, and you say phi of x is equal to x for all x in Q. Well, the reals are complete because you guys are taking real analysis. It will be made real to you in that course. And I stand by that. let's see here, and then, I mean, I don't know, the distance function is, I mean, d hat, right? So like, the distance function here is literally
Same thing.
the same distance function, just restricted to the rationals, so the condition of 1 is pretty much immediate. And the rationals are dense in the reals, so there's your example. But I have used this. We actually used this in my research at one point as a graduate student. We were studying something called well, let's see here. You could I suppose call them. I'm trying to remember which point it was. We did this, but at one point we thought about algebraic supernumbers. So be something like polynomials. So I don't know. It's hard to. I don't know if I remember enough of the details right off the top of my head, but something along the lines of like alpha 0 plus alpha I eta I plus alpha ij eta I eta j plus da 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 plus alpha ik, let's say eta ik, such that man, I can't remember quite the deals, but we use this idea to complete these things to get a larger set of supernumbers. We actually use the completion as a way of producing more of them. I can't quite remember what our ending point was. I don't remember. I mean, we didn't go from like rational coefficients. We always had like real or complex coefficients to the supernumbers. The completion was I think going from basically like polynomials. So you could look at things like this where you had finitely many non-zero, and you could have in principle you could have sequences of those which converge to something that had like infinitely many non-zero, so it would be outside the space. I'm trying to think of how that would go. Something like, your sequence could be something like Zn equals to, say, alpha naught plus, alpha, well, let me be more specific, say 1 half plus 1 over 2 squared eta plus 1 over 2 to the cubed eta 1 eta 2 plus plus 1 over 2 to the n eta 1 eta 2 eta 3, and so like the norm of this thing is something like, in our setup, it's something like 1 half plus 1 over 2 to the 2 plus 1 over, it's basically the 1 norm, picks off the coefficients, right? And so as n goes to infinity, that doesn't blow up, geometric. So it converges, and yet the limit point is outside the set of polynomials, quote-unquote polynomials, things that have finitely many non-zero coefficients. But if you take the completion of this set, then the limit point would be in there with infinitely many non-zero things. So if you can prove a bunch of stuff about polynomials of basically finitely generated supernumbers, then whatever you know from analysis that passes through the completion, you get for infinitely many supernumbers that have appropriate coefficients. That was one thing we thought about. I don't know, wasn't the last thing we thought about, but So this is something you could use if you're more adventurous. You could actually look at completion. You could build something with finitely many things and then like form the completion of it to get further. You could probably wonder what supernumbers are. That's fine. These etas are so-called Grassmann generators, like eta 1, eta 2 is equal to minus eta 2, eta 1, among other things. So if you have like an even number of etas in the expansion, it's something like an even supernumber. If you have an odd number in each one, it's like an odd supernumber. The odd ones anti-commute with other odd ones. The even ones commute with everything. And but anyway, I'll tell you more about that some other day.
So it's sort of like a mixture of like symmetric and anti-symmetric tensors.
Yes, but it's unending. It's part of what that Grassmann example I told you guys about interests me. I want to work that through. Okay, so that's a completion. He's got a few interesting theorems about completions in here, but I'm going to go ahead and... the function spaces theorem section, I'm going to skip past that. It's something that combines equicontinuous and pointwise totally bounded. That theorem 6.54 seems interesting, but these should go on. That brings us to nets. I don't have a good example for you guys, so I don't really know what to do there except to just tell you maybe the definition here and try to prove a theorem or two perhaps. Yeah, let's try to spend about 10-15 minutes on this, see where we get. Okay. I still got to go over the handout my brother has for you. Do you guys hit the 5:15? Is that okay? So in these super numbers, like even the numbers are like power series of things that have somewhat complicated algebraic structure. So like the concept of what a number is, it's really kind of interesting. I don't know.
Wait, so for example, if you had like fx, polynomials, coefficients in a field, and you took their completion, would that be like power series in that field, essentially? Like formal
I guess
power series that converge?
The question is, what's your notion of distance? To take a completion, you need to have a metric.
Well, there's a metric that you can derive from the field, I believe. Like you can treat fx as an ordered field.
Yeah, I don't know. I don't know right off the top of my head about that. I probably should. I will say this, he cautions us in here that the notion of completeness is not a topological notion. You can have spaces which are homeomorphic. You can go from a space which is not complete to a space which is complete, or vice versa, using a homeomorphism even. It's not preserved, it's not a topological trait, it's a metrical one. So, okay. That's a good question to ask then. I don't know right off the top of my head. Definition 6.55. Let's see here. An ordered set is called it's I, and it's got less than or equal to. Okay. It's called directed. When for every I and j in the set I, there exists h in the set I such that what? H is greater than or equal to I? Don't forget that question.